Hello, everyone. Thank you so much for being here this morning or this afternoon, depending on where you are. My name is Pete Vandersloos. I'm with Leifeld, USA. We have a limited amount of time, so I will go ahead and just dive in. I look forward to answering any of your questions at the end of the presentation. So, a little bit about Leifeld. Leifeld is we are an industry-leading supporter for CNC machine tools, been around for quite some time. I'm having problems seeing my screen, I apologize. So, I'm seeing if I can reorganize things. Sorry about the delay. So, we've been around since the late 1800s. A big focus of ours is being customer driven. As far as our solutions go, we do what we can to supply what our customers need, as opposed to coming up with a solution and then going to market with it. One of the big things we are dedicated to is confidentiality, research and development, and we have locations all around the globe. Our headquarters is in Aalen, Germany, which is in the Rhine-Westphalia region. Leifeld USA is headquartered out of Livonia, Michigan. We also have offices Moscow, Japan, and Shanghai. Japan is where our parent company, Nihon Spindle, is located. So we do our best to cover these areas with these locations. So a little bit about our timeline. So while we started in 1891, we got into the metal spinning world in the 1930s. And then we went to the very first hydraulic spinning machine in 45, first NC controlled machine in the late 60s. And then we followed along with what we discussed earlier, which is the customer-driven solutions. So starting in 1972, gas cylinders or pressure vessels, weight optimized wheels in the late 80s. Automotive components we started producing with our machines in 1992. Our longest flow forming machine was created in 2010. And then 2012, we introduced our machine which produces light poles and flag poles. 2013, we expanded our flow forming. And then in 2017, we started our digital simulation processes. The markets that we cover are not limited to, but mostly encompass the automotive, aerospace, energy, and industrial applications. There are many that cover more ground than this, but these really take care of a majority of where our machines are located. So our technologies, a lot of people are not familiar with our technologies. Metal spinning, shear forming, flow forming, profiling, and necking in are the 5 technologies that really encompass what we do. Today, however, we're just going to concentrate on these 3. Again, because of time and just because it can be a lot to see everything that we handle. So metal spinning is the oldest technology. Metal spinning is actually originally used in a number of different ancient cultures, but this is a little bit of a different situation because this is a CNC controlled metal spinning situation. So wanted to make sure that these don't have any volume, but this is how metal spinning works. You have a disc or a cylindrical blank. It is clamped with the tailstock to the spindle face and the tooling. And then the spindle rollers come in and they move in and they shape this over top of the tooling. This particular one that we're looking at is a 300 series stainless part. And it just shows you quickly how the spinning steps that are programmed in there that are taught in by the operator and then turned into an NC program. This is basic metal spinning. We start with a machine that makes a 500 millimeter part all the way up to over 5 meters. Flow forming is a different operation. Easiest to see it in an animation, which is what we have here. So you have 3 or 4 rollers over top of a mandrel. Your preform is spun and then brought through that machine, and it is stretched or flow formed into the dimensions that you want. Many different versions of this. You can have constant or varying wall thicknesses. And this shows, in this particular situation, how you essentially can double the size from your blank to your flow formed finished part. What I'm going to look at is the necking in process. Necking in is the process that we use for the production of pressure vessels and gas cylinders. In this case, there's a preheating operation. It can be done by fire, or it can be done in a variety of different ways, including induction heating. Variety of different materials can be used. Sorry, I'm having some issues. That's the preheating operation. It comes in from there, automatically brings the part over to the machine itself, loaded in, set to length, and then the forming process and the heating process continues. This is one of those workpieces we have all seen many times in our shops and all over our world, but this is how a gas cylinder is made. And it's always been made through the necking in flow forming process. So with these 3 distinct technologies that we're reviewing today, the question is, why did we name our presentation Stop Making Chips? Because we don't make chips. All of our processes are chipless. There's not a better way to say chipless, but typically in manufacture, we make a lot of chips. All of us, when we do machining, we produce chips. We, however, at Leifeld, take this in a different direction. So traditionally, we manufacture like Michelangelo sculpted. I don't know if you're familiar with this story, but Michelangelo was asked by the Pope about how he did what he did, particularly the statue of David, and that which is considered his masterpiece. And Michelangelo said, it's simple, I just remove everything that's not David, which is what we do typically in manufacturing. We know the part that we want to create. We get a block of material or a, whether it be a round, square, whatever the material is, and then we remove the parts that we don't want. At Leifeld, with the forming technologies, we do the exact opposite. So there are some advantages to that. Number 1, cost savings. If you're in the aerospace industry, you're familiar with the term buy to fly. And what that means is the material that you start with is the material that ends up in the part. To have a buy to fly ratio up to 60 to 70% is significantly higher than your traditional machining processes. In fact, when it comes to waste reduction, as much as 85% of the preform by weight is in the final part, which again, if you walk through your average shop and you see the amount of chips that are in the chip bins, it's quite a bit more than that. And the big advantage of that is environmental, which also results in a financial impact. Process improvements are improved quite a bit because what we're dealing with is a near net production. This is not something where we need to have significant secondary operations. And also there is no welding or the associated testing that goes with welding, because we're making our parts out of one continuous piece. And because of that, we're reducing the cycle times and significant more cycle times with the reduction of the secondary. The strength, the quality, because of our processes, because of the cold forming process, the material strength and the properties of the material are improved. We can talk about that for quite a while, but and we can go into quite deep in the weeds on that, but suffice it to say that the material is strengthened because it's compressed, it is stretched, it's moved in lots of different areas. The tolerances are still very, very good. Again, seamless. We can have different wall thicknesses, and the critical structure is always maintained. The other advantage that we want to talk about today is the weight, the light weighting, which is a very big key in what we're doing these days is very important because of the increased properties. We can go in thinner wall thicknesses, and because of that, there's also environmental impact. So, case study that we want to talk about today is regarding rotor shafts in electrical vehicles. By the way, at this point, if you think you might have a question or two, please feel free to type it into the chat box so that I can answer that at the end of my presentation. So, e-drives. You will likely and have already seen many slides talking about the market, how this is growing. This particular part, again, a customer-driven situation. A customer came to us and said, we need help in the production of the rotor shaft, which goes into the rotor that we saw just in the previous slide. So the typical types of the rotor shafts are either multi-part that are welded together, or fully machined from a solid or a tube. That is what has been done. Our customers came to us with a couple of goals. Number one, they needed to be lighter weight. Number two, they needed material savings. You needed to reduce scrap. They needed to improve strength and durability. And the solution that they had required a number of machines with a high capital investment and quite a bit of floor space. Those were the goals that were given to us by our customer. So what we did, because of our processes, like we just reviewed, we're able to go through with a complete process to produce these from a single part. And we were able to go through these aforementioned, and we were able to tick off every box. And obviously, when you're producing a new process that's never been done before, there are always challenges, but over a number of months through our research and development, through our engineering processes, we were able to come with a complete solution for this. So what we're able to do is offer to our customer that we have different types of preforms that they could use, a forged, solid, different types of tubes, or a disc. Now, us being the experience that we have, of course, the customer is always right, but we are still a German company that will always make a recommendation as to what we feel is the best way to go for the customer, dependent on their goals and the inherent processes and the part specifications. So we use the flow forming that we mentioned earlier on the cylindrical part of the shaft, and then for the necking in processes on the ends. In both situations, when we did the process, we processed from the rear direction on the first and second side in order to reduce the wall thickness, maintain the strength, and have a lighter weight, accurate part. This is a quick video of what this process looks like. That's a preheated part. So as you can tell, the process time there is quite quick, particularly when you compare it to what we know as traditional machining. If you were to think about this as a solid bar or a tube that needed to be machined, that would the cycle time obviously is quite a bit more. I'm going to turn up the volume just a touch so you can hear what the machine sounds like, and we can watch that one. So that is the how the one step of that process looks like. So the goals that we reviewed earlier, weight, scrap, quality, material savings, durability, all of those were attained. But the lightweighting and the cost reduction were the most dramatic. So if you consider the current situation where it was a forged part and they were machining, and this is, again, these dimensions are just for a case of example. With a solid part like this compared to a necked-in and flow-form part, we're looking at a weight reduction of 43%, which our customer was thrilled about and exceeded every expectation that we had hoped to attain. And the cost reduction was 30% less. We were able to produce the parts that they needed with less than half of the machines that they were originally planning on doing. Save them a good amount of floor space, not to mention all the savings that were made with electricity and other utilities. The machines that we used was our FFC machine, which we have in a variety of different configurations, which can do a variety of different technologies that can be applied on this machine. This is a machine that we have used for many years in the production of transmission parts in the automotive industry and other flow form parts. And then the machine for rotor shaft production that is also used in line with that. Because of that, we were able to attain all of these different benefits. Because of the ways that our machines are made, while oftentimes in a situation like this, they would be used for one particular part, they are still very flexible. So they can be continued to be used after that production run and rededicated toward another part. We can align these machines to whatever needs to happen regarding the preform. So if there is a specified preform that the customer has decided needs to happen, we can accomplish that. The floor space requirement is substantially less because of our compact machine designs and the way that we lay it out. So we were able to, with a 6-machine cell, produce 450,000 annual volume of these shafts. The weight optimization goals and the stability of the part were exceeded. Number 5 is interesting because of our ability to flow form. We can actually offer our customers the opportunity to look at a different design improvement. We can put outside grooves, and there is an opportunity so that it improves the cooling of this shaft, something our customer wasn't even considering, and they were able to go to the manufacturer of the vehicle and provide that as an option too. Saved an amazing amount of material, and we also reduced the secondary machining operations. So this has been a very quick overview of what it is that we do. So I thank you very much for your attention. Thank you for the opportunity to share this with you. I had to go through this quite quickly. So I'm just trying to give a little bit of an overview about what it is that we do and how we do it. So if there are any questions, please feel free to type them into the chat box. Okay, I have one question. Do you have machines that you have in your research and development department that we can do testing on? Yes, we do. We have flow forming. We have machines for wheel production, as well as metal spinning machines that we have in our facility in Allen. And we do testing on that on a regular basis. We also have the ability to do part and process simulations. That's something that we do. That's a very, very busy department because oftentimes we are just trying to prove out the ideas of a customer that a customer might have. So that's what we do. I mean, the types of parts that we do obviously are round. They are cylindrical, and they are. I mean, it's obvious to see the types of parts that we can do, but obviously cubic work pieces are not in our world. We're round part people. So if we got a customer that has an idea, we can do the simulation. We can also run parts for them. So the next question I see is, how do you know if a part is a viable option for Leifeld? Again, you know, the round parts obviously is the key. But if there's a situation, we have a list of all the different parts that we traditionally produce, whether it's from spinning, flow forming, necking in, or what have you. We have that on our website, so it gives you a very good idea of what types of parts we currently produce, whether it's in full production or whether it's in a job shop situation. We have shops and customers around the world that use our machines, and each machine can be used to make hundreds and thousands of different parts, and we have other machines that are set for production. So we always have a close relationship with our customers, so also we use them as a point of reference and as a resource for our other new ideas and projects as well. Someone asked a question about our target markets. We have a variety of different markets that we spend time in, that I reviewed earlier: aerospace, energy, automotive, industrial. Obviously, in the last year or so, we've had quite a bit of changes in our market, and difficult to predict, but we see a lot of opportunities in aerospace because the lightweighting and the material savings is a very big target for our aerospace companies, whether it be aviation or aerospace. Both of those are consistent. So they want very high quality products, obviously. The seamless and lightweighting process is a very big part of what they do. So that trying to look. Someone asked, can the process be applied to smaller pieces, say battery cell cases? I'm not familiar with what a battery cell looks like, but our processes can be supplied or can be applied to smaller parts. For instance, brake cylinders. We do a lot of those, a lot of production of those, and those are usually around 20 to 30 millimeter diameter. So the size of the parts certainly can be applied to our processes can be applied to smaller parts. That's not a concern. It usually comes down to whether or not there's enough production to justify it, and that's usually the case. I don't see any other questions. I don't know if Ahmet is still on the chat or not.
I cannot see any questions now. Pete, have you final words to our participants?
Thank you very much for the opportunity to chat with you. This is a very interesting world. I know that there are a number of you out there that I can't see. My contact information here is at the bottom of the screen. Please feel free to send an email or give me a call with any questions that you might have. And I hope that this day is an excellent one for all of you. Thank you again.